But it turns out the same technology can be used for many different types of applications. Where you want to understand things that are happening together. The idea was to recommend a situation where we think there could be a potential burnout or a potential failure. So the recommendation engine is trying to do predictive analytics and predictive maintenance for us. So again, you can use this technology for many different things. The real challenge is that we have a lot of users, a lot of items, but the data is sparse. You're going to have millions of people, millions of items. You're not going to have a lot of data in that type of a space. Types of recommenders. The first one is pretty straightforward. A person reads an article. There are similar articles, and we just simply pass that back to the user. This is your typical type of content-based filtering, where basically it might be something more like a library type of situation, where you're basically finding similar articles. The next one's a little bit more interesting, the user collaborative filtering. You have a person that buys or they rate an item. I rated the pizza, I had 3 stars, I rated the apple at 5 stars. Well, if you have another person that rated these things fairly similarly, the conclusion we would come to is that, well, these 2 users are probably similar. Okay, so how do we make a recommendation out of this? Well, if this person says, well, I want to buy a beer, obviously, if this is a similar person, we just recommend that to the other person. So this is the type of recommendation system, user collaborative filtering. One can argue that these systems have been around for a long, long time. There's a lot of research on this, but one can also see that sometimes they're really not as practical in many situations, and we can see this a little bit later. What we want to talk about today, though, is more focused on what's called item-based filtering, where I have a person that interacts with several different items. I have another person that interacts with a few more items. Now, what's interesting is that these interactions are effectively creating some sort of relationship. Now, I got 2 sets of relationships. So this person says, well, hey, I'm going to go buy a beer. We go ahead and recommend the apple because that's been also purchased by the same 2 people that also bought the beer previously. If you take a look at the user collaborative filtering, a person has to have a history of doing similar things or doing things before you can find similarity. Here you notice this user does not have to have similarity to the other user in terms of a purchase history, but instead the person just decided to buy something that does have some interactions associated with it so we can get an actual recommendation without having a larger history. So there's many advantages to moving to this. Challenges, data skew, very popular items. What if everybody bought the same thing? If everybody decided to buy the most popular thing, you really want to recommend something everybody already has. Very popular users. What if a person buys everything? And I mean, Granger would love it if somebody came and bought everything in the entire catalog. There's 1.7 million products, we'd love that. But it doesn't really tell you what to recommend because they bought everything. We're going to have to deal with this with normalization, interesting relationships, and data grooming. But what data really accurately reflects human preferences. Okay? Unfortunately, human-based references don't work really well. If you ask somebody, so what did you think of this movie? They're going to tell you something, but maybe a half hour later, they're going to tell you something a little bit different. Maybe the next day they might remember that they liked something about the movie better. So what ends up happening is that basically asking people of their personal opinion about something is usually not a very good indicator of what they really thought of it. I know that's kind of a strange statement to make, but that happens a lot. What's more important is watching what people do is far more powerful than having them record what they say they like. So basically, we want to get to the point where we can say, okay, we're going to start looking at the behaviors, what people have done, rather than what they say they like. So it's a little bit different take on this, which is what the item recommender does. Raw data, item interactions. On the right, there is a random data set. I just generated a bunch of users, a bunch of interactions. So I've got 4 users. I've got 7 different interactions with fake products, so there's 8 different products. So what we have on the left, we have the fact we have 2 different users, user 0 and user 1, and they interacted with all these different items. So this is the use case that we're looking at. Now remember, the interaction could be many different things. It could be, well, maybe they shared something, maybe they bought something, maybe they viewed something. So again, there's some kind of interaction taking place between people and these different items. So you can see that we have this data set here on the right that we're going to be using through the rest of the presentation. But this is the general idea of having interactions and items. The first thing we're going to do is introduce everybody to some mathematics. This is a matrix. I think everybody remembers this from high school. It's that stuff that nobody liked, that linear algebra class. Everybody says, well, what do we ever use that stuff for, right? Okay, that interaction, those interactions that we saw, we compress all the stuff vertically. You can see on the left we have the users, and across the horizontal we have all the different items that they interacted with. User 0 interacted with items 1, 3, 4, and 7. Yeah, look at that, we're halfway there, right? Matrix, it's not that hard to understand, but you can compress your data set into some more useful representations like this. Okay, what can we do with this A matrix? Okay, let's define another matrix. By the way, why do they call this history matrix A? I don't know, but if you see it in all these references, you're going to see it be called A. So I'm just going to use the same nomenclature, so in case you look at a bunch of references, when they say A, that's what they're referring to. Here's another one. They call it H, which is the current interaction matrix. Now, I mean, why do they call that H? Okay. Basically, if I'm on a website and I've interacted with product number 4 once, that's what that matrix is telling us. Again, not very complicated. Our hypothetical system has got 7 or 8 different products. Somebody interacted with product number 4 once. So now we have all these interesting things we can do with these matrices. Our A matrix will translate items to users. You take the transpose, it will actually convert users into items. If you multiply the two together, it's going to tell us how many users interacted with the items, and we're going to see this in a moment. But the bottom two is where we want to get to. The first one is the user-centric recommendations, which will basically tell us, given users, what do they recommend. And the last one is actually called an item-centric recommendation, which is basically given items, what items do we recommend. So 2 different sets of mathematics. We'll see that they're very important because we do some interesting things with it. Okay, as promised, let's multiply some of these things together and see what we get. Okay, so I take our current interaction matrix, which we just saw. Again, all it is just users and items. We just compress that data set. Multiply by H, and what do we get? AH says, well, if we interacted with item number 4 once, AH tells us, well, that must have been user 0 and user 2. So basically, users 0 and 2 have interacted with item 4 once. So you can see what's happening here is that we can get at some interesting information in these data sets just by some simple matrix multiplications. Okay, very simple. Took the A matrix, multiply it by the interactions. We can say, here's the people that actually were playing with those particular items. So let's now convert that into a recommendation system. So basically, if we take the users that were interacting with something, and we multiply this by A transpose, it turns out we get this matrix in the middle, which basically is a recommendation matrix. Well, if you take a look at this, excuse me, we know somebody interacted with item number 4. We know that that was user 0 and user 2. Multiply this together, what do we get? Well, it says product number 1 has the highest weight of 2. Product number 2 has the next highest weight of 1. Product 3 and 4 also have a weight of 2. What's doing is giving us weights. It's telling us what kind of interactions have we had with those products based on who was interacting with it. So what users have been interacting with. Now, you could have easily seen this if you look at the data a little bit more carefully. Take a look at this. User 0 interacted with 1, 3, 4, and 7. User 2 interacted with 1, 2, 3, and 4. So if you take a look at that result, we see item 1 occurs in both data sets, both users, so therefore that gets a score of 2. Item 3 interacted with both user 0 and 2, so that gets a weight of 2. Item 7 occurred only once with user 0, so therefore that's lower weighting. So what we're really doing is we did a couple of matrix multiplies. We have a recommendation already. We have a recommendation engine that says, hey, here's how many people have interacted with these products, and here's the weighting on their interactions. Voila, we have a recommender. You may not get a lot of business with a recommender like this because it's kind of cheesy, but it does work. Believe it does work. You can do this. So let's take a look at what we can do to make this a lot better and a lot fancier, a little bit more accurate. A lot of interesting stuff on this slide, but let's take a look at what's going on. We got this user-centric recommendation on the left, A transpose AH. We got item-centric A transpose AH. But notice the order of operations is different. Okay? On the left-hand side, we do AH first. Now remember, H was our input vector. I don't know why they call it H, but that's our user interaction vector. But what's happening is that we can't do anything until we do that first multiply by the user vector first. Whereas we take a look on the right-hand side, A transpose A, we can pre-process that. I can process that overnight, and then when we get that H vector, I can multiply and have a result really, really quick. This is why we usually don't see the recommenders on the left, which we just got done taking a look at. We want to explore what can we do with the recommender on the right, where we can pre-process a lot of the data, and then we can store that entire matrix, then we get our interactions. Given the interactions, we very quickly come back with the recommendation result. That's really what we want to do, because that's going to be your fastest result. And that's why we do this order of operations a little bit differently. So let's take a look at what we can do. An item-centric recommendation using Co Occurence. It sounds really fancy. Matter of fact, you start saying stuff like that, people might think you're really important. So what we have is an item-centric recommendation system we want to put together. You'll see these talked about a lot in the literature. What's going to happen, though, is that they don't usually give you all the mathematics to understand how it really works. So we're going to go through that. There's a lot of details. And if you see the order of the operation that we want to do, you can look back at the mathematics at some later point in time to get all the details. Okay, so co-occurrence recommendation. So basically, recommendations are based on similar past behaviors, not just the similar users. But why do we want to do this? Well, it's easy to understand. The Java simulation is only 10 pages. So my slides in the Java code, by the way, is freely available if anybody wants it after this. It's easy to implement. Now here's what's interesting. There was a discussion where somebody actually implemented this on a microcontroller. A recommender on a microcontroller, isn't that interesting? An embedded data processor on a little board computer. So basically, you don't need a gigantic Hadoop cluster to do this. Again, it's the mathematics and what kind of situation do you apply it to? That's what we want to look at. We don't want to have to take a look at some kind of gigantic simulation. We want to say, what's the technology? What is the technology? What can it do? It's extensible. We can do things like multimodal recommendation. If I search for music, it'll say, what about these movies? You can do some interesting stuff like that. Streaming recommendations. As people are buying things online, you can immediately update your recommender to start using that information immediately. So you do some really interesting things with this. Co Occurrence matrix. Okay, so what is this? We're going to introduce another matrix here in a moment, but it's a simple way to represent events that occur together. Co Occurrence. Okay, we're thinking about things that happen together. The question is, which things happening together are actually really important? Now, this is interesting. Now, I'm saying a lot of unusual words here. It's interesting, it's important, it's unusual, it's anomalous. How do you attach a mathematical relevance to things like this is interesting, or this is important, or this is what we want? Think about what we want to do is get to the point where we attach some sort of mathematical relevance to our interpretation of something we think is just really important. Okay, so let's show how we can do this. A couple of steps. The first is we're going to have our raw data. We already saw that. That was that huge listing of random stuff I put together. History matrix, we already saw that. You compress it down. That gives you basically users and items. Co-occurrence matrix, this is what we're going to introduce now. A new matrix, and it's really easy. It's A transpose times A. I think everybody did A transpose somewhere in high school, and you did that matrix multiply. So all we're doing is saying that the fancy name of this matrix is really called the co-occurrence matrix. It's nothing more than multiplying a transpose times the matrix itself. Fairly simple mathematics, but the question is, what is this matrix telling us? What it's telling us is this. We're taking a look at this when we say, okay, this is the A transpose times A matrix. So basically, take a look at the intersection of 4 and 3. What it's really telling us is that the number 2 says there's 2 users out there that had interactions with both 3 and 4. So it's an interesting question. That 2 tells us this. When we take a look on the right, we'll see that we have our original data set, and you see there's 2 sets of users, user 0 and user 2, that both interacted with 3 and 4. So you see, just by using some matrix operations, we can actually find some interesting information about what's going on with this data set. And again, this tells us now that we had 2 users that were interacting with us. It doesn't tell us which 2, it just tells us that there were 2. Okay, so that's really important. So this leads to, this leads us to 2 types of this leads us to 2 types of recommenders using co-occurrence. Excuse me. Okay. So we have what I'm going to call a current interaction recommender. I'm currently interacting with something. I want a recommendation. But we also can create another type of recommender called the anomalous relationship recommender. What this does is says, I don't really care what you're playing around with right now, what you're interacting with. What I want to have is a list of things that are unusual based on past history. Okay? So this is an interesting thing. Again, how do we define interesting? How do we define unusual? How do we define this is important? Very interesting mathematical things. We'll get to this in a moment. For those of you who want to build systems out of this, we're really looking at 2 different types of systems. On the top, for a current interaction recommender, we do have to deal with the fact that on the web tier, we get a product request. Normally, you dig through your search engine, find your information. But we're going to have to call another box which says generate the recommendations. So on your input information, we're going to have to generate a recommendation for that. So that is another real-time step that we have to do. If you think about the fact that we've got this co-occurrence matrix and this other matrix, and the first one's been pre-computed, that's pretty fast. So it's pretty fast, but you still have to do this other step. The step on the bottom, the system on the bottom is a little bit more interesting. We're again going to create this matrix called co-occurrence. We're going to create something called importance anomaly indicators. So again, we're going to have to get to a mathematical expression that says this is important. So how do we do that? So basically, when you find your product, what the bottom recommender system says is like, wait a minute, these things are also really important. And then you attach that as your recommendation. So again, we've got to get to the mathematics that shows us the concept of importance and things that are interesting. But this is basically covering what I did just for reference. I am adding the fact that we may use this thing called cosine normalization to reduce some data skew. But let's take a look at this. So this is one of the systems I just introduced. Let's go ahead and do the multiplications and see what we get. Okay, the co-occurrence matrix we took a look at. We got our item interaction matrix. We saw that item 4 has interacted with once. We multiply these two things together, and again, that matrix on the left, you can pre-compute it. You can pre-compute that and store it. You don't have to worry about that being done in real time. Take a look at what we got on the right. It looks very similar to what we got in the first recommender, doesn't it? The first recommender, remember, did the operations in a different order. Multiplied H times A, then times A transpose. Here we're multiplying A times A transpose, we're storing that, then we're multiplying it by H. So it turns out we're doing a different set of operations, different order, but we got the same result. Well, almost the same result. Notice item 4 came across as a 0. There's no reason to recommend something we're already interacting with. That's simply done by zeroing out the diagonal. Again, a lot of things you can play with. But again, we got basically the same recommendations. And the reason is that, again, we're dealing primarily with counting here. Now, counting sort of works. I'm going to say sort of works. You can get a recommendation, but you're counting. Counting is not always very good when you're trying to recommend. But we're going to modify this so that it gets a lot better. Cosine normalization. All I have to do is say, gosh, I know cosine normalization. It's like, cool, give the guy a promotion. Basically, cosine normalization is fairly simple. You'll see it a lot in almost all big data processing. All it is saying, I've got these two different vectors. How different are they? The interesting thing about cosine normalization, it basically says it's the cosine of the angle between them. So that's going to be between 0 and 1, fairly simple. So we get a measure of how similar two things are. It's going to come out to be 0 and 1. So again, think about it. You've got two different vectors pointing in space, your simple geometry, your plane geometry. You got two lines, and you ask the question, what's the angle between them? That's what this is. That's all this does. It's very easy to compute. The numerator actually is part of the matrix multiplication. The denominator, the square root of the sum of the squares, I think we've heard of the Pythagorean theorem before, right? So all we're doing is basically a length. We're just dividing by the length of the vectors. Again, normalization, we're just dividing out some lengths. This is very important, though. Again, it's used in a lot of big data processing, and we'll see that it helps us through some interesting situations. Okay, so let's take the previous result and use cosine normalization. You can see what happens. On the left, we're using just counters. On the right, we're actually taking this and cosine normalizing it. But what it's telling us is that due to some of the data skews and irregularities, it says that actually 1 and 3, even though they have the same count on the left, that 1 is actually just a little bit more important than 3 is. So now we're starting to take a look at what happens when we start normalizing the data. We see it's not just a bunch of counters, but we can start normalizing this to say, well, how relevant are some of these counters? So now we're actually going to be splitting this between two things. And as promised, here's some Java code. Oh gosh, look at this. We have the dot product. If you take a look at that, that's your inner loop, a matrix multiply. But take a look at this. I've added 3 whole lines to this. Namely, we're summing up the squares, and then we divide by the square roots. Now that's not too hard to do, right? That's the Pythagorean theorem, that's normalization. But notice what it did. It gave us a finer resolution on the scores, which is telling us more information about the data because we're normalizing out the counts to actually get to something that's a little bit more important at this point. Okay, let's take a look at an interesting issue. What if all users buy item 0? Let's say everybody bought the most popular product. Do you want to recommend something that everybody's already seen? Probably not. It's a recommendation, but why recommend something that everybody probably has already seen or already knows about? So again, this is where the cosine normalization comes in handy. I modified the data set so that basically all the different users, which are 4, I added an extra line so they would all buy item 0. If we take a look at the left, we saw the effect of cosine normalization. We take a look at the right. What ends up happening is that we start seeing user product 0 having a count of 2. So it turns out all sum product 0, which initially had 0, now has 2. So therefore, it's just as high as the other ones were on the top. So if you think about it, everybody bought the same product, so now we're going to recommend it. However, if you cosine normalize it, it turns out that that actually goes away because it's now a large vector of information, but it's not really that relevant. So you divide by its length. What happens? That 2 now goes to a 0.28. So it turns out that even though everybody bought product 0, the cosine normalization moved it farther down on the priority list because basically it's a long vector of the same information, but it's not really that relevant. So again, cosine normalization is used for a lot of things. This is where the cosine normalization actually is getting rid of some of the problems with data skew. So it's a very useful thing. The reason I bring this up is you're going to see this all over the place. Almost any search engine you look at, you're going to see cosine normalization. Comes in handy with a lot of things. What if user 0 buys everything? Well, I think that'd be great if somebody came into the company, bought every single product that we had. That'd be wonderful. But then again, a person doing that means they're really recommending everything because they like everything. They bought everything. Is that really relevant to anybody? Probably not. So again, we take a look at what's happening here on the popular user. The original recommendation now shows that everything is being recommended. Everything has a non-zero score, except for 4 because we zeroed that out. But if we cosine normalize this again, notice we have the same ordering of 1, 3, 7, and 2. We also have non-zero scores for the other one. However, they're not very high in the priority list. So again, the cosine normalization did kind of normalize out some of these data skews that we've been seeing. Again, very important for the normalization. So now let's take a look at something that's really cool. So again, all this stuff works. It's all counter-based. Do we have statisticians and data science people in here? Some of you? Anybody? Can I embarrass anybody here? Okay, so if you think about it, counters are great if you're doing statistics. I count this up, I divide by this, I normalize by that. I mean, statisticians, statistical analysis, I love to normalize everything to 1 or something like that, right? It turns out that that does work for the system that we previously saw. However, it does not get us to this fabulous question. How do you define something that's important? How do you define something that's interesting? How do you define something that's relevant? Let's take a look at how do we get to that. It's going to take us away from the field of statistics to another interesting field on information theory. And I'll show you what we can do with this. Okay, this is an important slide. It's going to show us the journey into the field of information theory. These are all the different steps that we have to go through. The reason I'm showing this slide is that very seldom do you see in any reference a single slide that shows everything you need to do. They'll usually start with the history matrix and then say, here's the output, and leave all these mysterious things to some library. That's interesting, but what if you want to make modifications to that library? What if it didn't perform the way that you wanted it to? What if you want to make some different types of calculations? So you need to really know what these libraries are doing and how to use them. So what I want to do is drag you through all the mathematics, including the important mathematical step that says, here's when we know that something is really important and we have to pay attention to it. So we saw the history matrix already. We saw the co-occurrence matrix already. I'm going to introduce a few more things. One of these is called the contingency matrix. Basically, the co-occurrence matrix, we have all the different pairs of things that have happened together. The contingency matrix is created for each pair. But keep in mind that matrix is symmetric. We don't use the diagonal, so in the end, there's not a lot of computation there. Expectation matrix, I'm sure there's a lot of statisticians here. You have to have expectations somewhere to keep a statistician happy, right? If you're not doing expectation, you have to do that somewhere. Then we're going to go through this thing called the G-test score. Isn't that cool? Then we can go ahead and do some ranking, and then we're going to come up with this interesting set of pairs that says, well, out of that co-occurrence matrix, there's a lot of different pairs. Which of them are really important? And this is what the list on the bottom is. Out of that synthetic data set, we have all those pairs, but only some of them are actually really interesting. So they actually, I guess when I was creating it, maybe some personal bias might have been introduced, which created the fact that some of these are more related than just random probability. Okay, computations. We actually just went through this. Again, this is for other people to review at a later point in time. Here's a slide I borrowed from Ted Dunning. It's really interesting. I had a very interesting talk with him about some of this stuff. This is an interesting slide. It reference is to his presentation is there, so I pretty much copied it directly. But what conclusion do we draw from this? Okay, let's pick 2 different points in that co-occurrence matrix. Pick any 2, 0 and 3 or whatever. I think I said 0 and 2. Okay, so A is 0, B is 2. A and B can be anything, any set of pairs. We create this thing called this matrix, which is the contingency matrix. Now, what this means, we take a look at the top left. It says A and B have been combined 13 times. We've observed them 13 times. So basically, whenever A occurred and B occurred, that occurred 13 times in the data set. We need to look at some other sets of information. A occurred without B 1,000 times. B occurred without A 1,000 times. Now, there's 100,000 other combinations that occurred that had nothing to do with A and B. Okay, simple question, is that important? I don't know, we'll find out in a minute. Let's take a look on the left, top right I mean. A and B occurred once. If we think about it, A occurred only with B, B occurred only with A. It's like, wow, they occurred together and nothing else ever combined with them. If we take a look, there's only 2 other data points. This basically has 3 points in the data set. So that means even though it happened once, they happened only together, they happened with nothing else, but it does happen 1/3 of the time. So again, is this important? Well, let's keep on thinking about this. Bottom left looks even more interesting. Same type of situation. A and B occurred with each other only once. They never occurred with anything else, but now we got 10,000 other things that have happened. Is that important? Is that interesting? Is that fascinating? Is that anomalous? How do we know? Take a look at the one on the right. Now this is interesting, because now A and B have occurred together 10 times, but now we have 100,000 data points. Now your typical statistician, and sorry if I'm offending anybody who does statistics, but you'll divide that out and say, well, there's 1 out of 10,000, and that's 10 out of 100,000, it's 1 out of 10,000. Those bottom two look a lot alike, don't they? Matter of fact, they look a lot like the top right, where basically it's just 1. So the real issue is we need to take a look at all these different things that are happening and come up with a more definitive measure that says, this is interesting for this particular reason. Okay, here's the scores. We're going to compute this G-test. The top left has a score of 0.9. Now, this score is like a standard deviation. So if you think about it, if you've got a standard deviation, the farther out you are, the less probable it is. So you can think about the fact that things that are important and interesting are generally things that are going to be less probable. If something's very, very probable, the sun's going to rise tomorrow, that's pretty probable. It's really not that interesting because it's going to probably happen. If it doesn't happen, I'm going to go hide and run in the caves, and I'm going to be gone. So therefore, we're looking at really the fact that probability is related to a lot of the stuff that's interesting. It's related to the information that we're seeing. So now we have the one on the top left. Well, that's got a deviation of 0.9, a G-score actually. The top right is 1.95. The bottom left is 4.52. And if you think about it, at the Large Hadron Collider, they declared new particle discoveries at a deviation of 5. So that's getting pretty close to being scientifically extremely relevant. But the one on the right is even more fascinating. Even though it looks like it was just a scaled-up version of the one on the left, that's way, way out in this teeny little tail. So basically that occurred, but it's extremely interesting. It's very rare. So one can take a look at this and say, are those two things really the same? On the left, we have one occurrence. Let's say you're in a city of 10,000 people. You see two people standing together. You see that happen once. It's kind of like a statistical aberration. Two people standing together, so what? On the right, let's say this same two people, but they stood together 10 times. That's really unusual, even though you had many, many more observations. It's really unusual for the two people to be standing together, and only those two people ever stood together. So therefore, the combination of that is much, much more interesting, which is why that score is much, much more interesting, even though statistically, you can just basically scale this up. Okay, so basically, let's take a look at how we can actually compute this. What we want to do is we want to start out by saying, get rid of the diagonal, and here's where A and B have occurred in the matrix. We can say, well, everything that is A but not B are these. Then we can say this is everything that's not A but it is B. So basically when I was saying, how do we get that information out of that matrix? Well, here's how we get this. What's really interesting is that we put this into this matrix on the right called the contingency matrix. You can see we just put the counters in there. So you count these up, the A, the AB, the A not B. You get this matrix on the right. And these are just simply counters. So again, we're looking at counters, but we're going to do something really fancy with this. What we're going to do is say, okay, we know what we've observed. We get a bunch of counters. The question is, what did we expect to get? Now this is where it gets kind of complicated. I'm going to just go through this, talk through this really quickly. For those of you who like the mathematics, I'm sure you like this. But basically, we know for A and B, we've observed it happened once. Assuming that these are statistically independent, is the probability of A times probability of B. That's what we would expect. But how do we get that? Well, probability of A is how many times A occurred, which we know A occurred with B, A occurred without B. So we just add that up. So what we're really getting at here, and I guess I can't really, maybe it doesn't work on here. So you see what's happening? We have 1 plus 2, we get 3. That's here, 3. 1 plus 7 is 8, and we get 8. And we divide by 21, which is the total. And the rest of the mathematics here just simply show that if you can estimate the expectation from the counters. But what's really interesting about this, and this is again where we start taking a look at the difference between statistics versus information. I observed 1, A and B occurred once. I'm expecting it to occur 1.1. For A and not B, it occurred 2 times. We're expecting it to occur 1.8. We have that B and not A occurred 7 times. We're expecting it to occur 6.8. And not A and not B occurred 11 times. We're expecting that to occur 11.1. If you think about this, almost all the observations happened with pretty much what we were expecting it to happen. So basically, if you're expecting it to happen, and it does happen, is that really interesting? Well, obviously it's not. I'm expecting it. So therefore, we have to take a look at the fact that this isn't a simple statistic. We Now we have to wrap that thinking. How do we actually convert, gee, I got what I expected, so therefore that's not interesting. Well, that's what this score here does. Obviously, if the observation and the expectation were the same, that log would give us 0. So basically it would drop out. So basically, if we get what we expect, it's going to basically tell us there's nothing useful there. So therefore, this score will tell us how interesting those 4 numbers are. As a challenge question for everybody, does that equation look somewhat familiar to something else? I'm multiplying something by the log of that something. Does that look very familiar to anybody? Whoever gets it right gets the USB drive with my code and slides on it. Does anybody know what that is? It looks a lot like something else. Please don't say the log likelihood ratio, because that was done in derivation, but it looks like something else. What is it? Okay, anybody? Anybody want to guess? Does anybody want my code and slides? I'll give you a hint. It begins with E.
Euler?
What?
Euler?
Well, he was a cool guy, but he didn't do this.
Oh, okay.
Is it the constant E, 2.71?
Not the base of the logarithm, no. Begins with an E. What does this look like? What does this equation look like? Anybody? I know one person knows what it is, right? Kyle?
I don't remember the name.
Okay, good. He doesn't remember it, so he can't get it, because I know that guy. I'll going once, going twice. Anybody recognize that? That's actually what's called in information theory an entropy measurement. We're measuring information with this. Basically, the total information is basically the scaled sum. But since we don't have the scale factor, well, okay, I'm just going to stop there. Basically, if you take all of those different situations and you make a scaled sum, you get the measure of the information. So if you think about it, if something is improbable, when it does happen, we get a lot of information. I like to use the statement, let's say Scott Kramer, I think we all know Scott. Let's say he's at the door standing on his head, whistling Dixie, handing out $100 bills, okay? That's a fairly improbable situation, right? But if it does happen, we've learned a lot of information. We know it's Scott, he's standing on his head, he's whistling. So basically, the information that you learn when something happens, if it's improbable, is you learn a lot of information from improbable events. So we're really trying to figure out, are we learning a lot of information from these things happening together? And that's what this equation is trying to tell us. So again, the equation itself is called the G-test. You'll see a lot of things sometimes calling this a log likelihood ratio. Ted Dunning did derive this from different types of situations, but in the end it tells us how interesting is this based on the information that we would learn if this really did happen. So that's what this equation is telling us, and that's why we're trying to get to this for our recommendation. So how do we use this? Again, you interpret this as a standard deviation. Use thresholds, take your top highest, however you want to do this. Here's an example. For the situation that I gave you of synthetic data, if we draw in 0.9, you'll see that we end up with basically 6 surprising relationships. So out of that entire matrix, only 6 of them really look interesting. This slide actually just gives you a little bit more numbered, but what it's saying is some of these had a count of 1, some of them had a count of 2. Some of those with a count of 1 are actually more interesting than those that had a count of 2. So again, basic counting will give you a recommendation. It'll tell you how popular something is. It's not going to tell you how interesting it is. So again, we have to think about the difference between popularity versus something being interesting. Interesting being defined in terms of, if it does happen, have we learned a lot of information from actually seeing that? And that's what we want to recommend to people. Adding this to a search engine is pretty easy. We have a search engine. If it basically has a request for something that we have a relationship for, you just simply return those relationships and say, oh, by the way, you're interested in this product, but here's a bunch of other products that are also very interesting that you might want to consider. G-test scores, again, I go through a lot of this stuff, but what ends up happening is that if everybody buys item 0, we don't have cosine normalization here. So if everybody buys the same product, it is going to skew us and say, well, here's a lot more surprising relationships because now we're seeing a lot more products being purchased. Same thing happens here if a particular person buys everything, all of a sudden everything is recommended because everything is interesting. So basically, these are some of the things that we're going to have to deal with. Performance considerations. What we really have to do is to think about how big these matrices are. Again, the Co Occurence method is very popular because you can pre-compute that. You don't have to compute that on the fly. So we really want to reduce the size of this matrix in order to help us get this computed. You can generally compute something like this for a fairly large catalog in just a matter of hours. If you're doing other things like gradient descent, you're looking at probably days to weeks on some of these calculations. But what we want to do is we can reduce this matrix size. We can remove the users who buy too much. We already saw that, if a person buys everything, it's really nice for your profitability, but then again, recommending everything is really not that relevant. Items that are too popular, if everybody's already knows about it, there's no reason to recommend it. So you start limiting these things, you start reducing the size of that matrix and reduce your calculations. The other thing is you want to also reduce your window to the last n interactions. You might have 5 years worth of data. You put all 5 years into the matrix, you probably don't want to do that because chances are market conditions have changed, user preferences have changed. A lot of things can change over the time period. You typically want to keep your matrix to a size that's more relevant to your business. If you're basically in the summer, you might find a lot more people buying things like umbrellas and suntan lotion. Winter might be things like shovels and salt. So basically, your recommendations may be seasonal. So again, you might want to limit your actual number of history times. Improvement breakthroughs. What kind of improvements have there been as far as breakthroughs for recommendation engines? I mean, this is really incredible, some of the stuff that's happened. Biggest breakthroughs you could ever imagine. Was it fancy mathematics, statistics, and algorithms? No, it wasn't. It's people taking a look at really some fairly simple things. Some of the breakthroughs were actually involving something called dithering, anti-flooding, and multimodal operations. I'll just touch upon these fairly quickly. Dithering. Basically, typical users don't look beyond the first page. They're going to take a look at your search results and say, I don't see it. Put in a different set of search terms. They don't scroll. Don't go to the next pages. So basically, your recommender is not going to stagnate. It's always going to be returning that page for those types of queries. So its performance is not going to get any better because people aren't buying anything different because they're not seeing anything different. So what do we want to do? We take our list and we take the log of that rank and then add some random noise to it and then just rescore it. So basically what we do is we want to bounce the items back and forth just a little bit, nudge them a little bit so that every time you get that page back, it's going to be slightly different. Your upper items will still be probably in the top ranking, but you may introduce items from other pages that are probably interesting that they probably never would have gotten to because they're just simply not going to do page flips. So this is actually a very important way of introducing a person to things that they may not notice actually on the following pages. Anti-flooding. This is really too much of a good thing. Basically, you give recommendations. Company I work for, if you say hammer, you're going to get a zillion references to hammer on your first page, guarantee it. Because there's so many of them. I mean, do you really want to see all of them? Well, what you might want to do is basically reorder the results to make them look a little bit more diverse. So what you want to do is penalize the rank of things which are highly related to those you've already seen. So if your first 3 or 4 items are a certain type of item, if the next 4, 5, and 6 are highly related to those that you've already seen in the top of the list, you might want to move them down because they've already seen those types of products. So again, a fairly simple step, but again, anti-flooding actually helps people find products that are related without finding the same thing multiple times. Multimodal, this is really, really interesting. This is one of the few recommenders I know that can actually be extended to multimodal computations. What do I mean by this? There's many types of interactions. Even a very simple website can have many different things. A person could be buying something, in which case you have a user ID, it's a buy operation, and an item ID. They might view something. They might have a category preference. Maybe they spent all their time looking in a certain category. They might have shared something. They might have done a search. So it turns out even on a simple website, there's a lot of interaction information that we can use to help us figure out exactly what a recommendation would be. So basically, what we can do is put all the stuff together, even on a simple website, to give us more information about the user's interactions. And think about this. If we were to try to ask the user, what's your preference in terms of sharing, what's your preference in terms of categories, it might be really hard to get information like that. However, if we look at their behaviors, what they've done, it's easy to construct a better history and get their information. So what do we do with this? Well, we can improve our matrix by making it grow horizontally. And it works like this. We previously saw the fact that we had users and products in a matrix. We saw that it was our A matrix. The first thing that we introduced, that matrix was just compressing the data down to a simple representation. What we now have, though, is the fact that, oh, by the way, besides actually purchasing that product, maybe the person viewed that product. Maybe they actually stayed within the same categories as they were searching for that product. Maybe they shared that product with somebody. Maybe they actually had certain terms that they were using while they were searching when they were doing their views and doing their purchases. So now we basically extend our matrix of interactions horizontally, and therefore we have an interaction which encompasses many different behaviors. If you think about this, this is just a larger A matrix. So everything I've just done still works. Take everything I've just showed you, use your larger matrix, and now you can go ahead and get a recommendation that uses all this past behavior. So a person could be maybe browsing music. While they're browsing the music, you could say, well, wait a minute, maybe you might want to take a look at this movie. You might want to say, oh, by the way, I shared all this stuff. Oh, they said, well, maybe you might want to go view this product. So you can actually get very interesting recommendations from all the different types of interactions that are happening. This is really one of the important reasons why people use co-occurrence processing, because you can extend it to basically occurrences of any types of behavior. Very interesting technology. Continuous streaming updates. If you think about it, if you're doing something like recommending music, you probably would like to take a look at what they're doing right now and have that recommendation ready fairly quickly. If you're doing something like news service, so a person is browsing for something like recent car accidents, well, you want to get that accident information into that search engine as fast as you can. If you think about it, many times out here on the metro, it's like, oh, there's been an accident on such and such track. Well, I can go ahead and Google it. It's like, oh, wow, look, they're talking about the accident already. It was only 5 minutes ago. Well, you got to get that stuff into your recommendation engine fast. You can't say, I'm going to generate my matrix. Oh, it's going to take about 5 or 6 hours or maybe a couple of days. It's too late. You got to get that information into that matrix really fast. So as people start searching for stuff, you can make the recommendation this is probably what they want. So what we want to do is think about the fact that that box in yellow, before it's set to batch create that, you can actually incrementally do this as well. If you think about it, at that point, that matrix is what? Just a bunch of counters. Counters are really easy to add to and subtract to, which is one of the reasons why this is a very popular method. You can do a lot with it. If you want to do incremental updates, you just simply add and subtract stuff from the actual counters that you're looking at, and then just let it flow through the rest of the system. It turns out because you're only making small changes, the things downstream actually do not always change, so this is really not a high computational load. For example, you might make a bunch of counter changes. The importance or indicators may stay exactly the same, in which case you don't make any updates. So again, it's a very fast way to get up-to-date and relevant quick information into your system. Additional reading, I put together some additional reading for people. Again, this is some interesting stuff. But again, you will see that a lot of these will show you here's the history matrix and here's the result. If you want to know more, just pay a consultant $300 an hour and you'll get that. But what I've done is show you that the technology is fairly easy to understand. You can apply it to many different things. And depending on the size of your project, if you don't run it on your laptop in a few hours, that might work. Or maybe go ahead and just run it overnight. Or if you need to, go ahead and set up a gigantic cluster and get it in a few minutes. So your implementation really depends on the scale of your data. But the technology doesn't change. So it's important to understand this technology, to understand how do you want to build, how do you want to deploy it for what you really want to do for your business purposes. So again, these references will again show you pretty much the first 2 or 3 slides, and it's going to show you the last one. But I gave you all the slides in between that shows you how to get from point A to point B. Again, it's good reference to go back and take a look at all the numerics, all the calculations, all the stuff happens. And remember, what's that important thing that tells us how something is important or interesting? What was that word I used? Began with E? Entropy. Entropy, yes. So again, the basics of a lot of what's happening with these recommenders is based on entropy, which is basically a measure of information. We're not looking at statistics, we're looking at information measurement. And it's actually a very fascinating field where, again, improbable events carry a lot of information when they happen. Okay, that's a very important thing. So we can start thinking about how do we categorize, or how do we relate back concepts of things that are interesting, important, back to a mathematical way to say, well, this is what's happening with the data, so therefore this is important. Okay, so basically, the last thing I have to say is that this is actually out there on GitHub. So all this stuff came from an application that I wrote. It's about a dozen pages of code. It's pretty easy. With a dozen pages of code, I created the 3 different recommenders. I have the cosine normalization. I do the calculation of the g-test. All that stuff is in there. So you can go ahead and take a look at that code if you want. It's all in there. And also my slides are available, but I'm not really sure how to distribute them. I don't want to have 200 people sending me emails tonight. So I'll try to figure out if somebody really wants this stuff, how I can distribute this. Okay, that's pretty much it. Again, I know it was kind of a whirlwind presentation, but the whole idea is to give everybody a more comfortable feeling of what's really going on here. Again, there's a lot of simple things you can do, and some of the simple things may work. You probably get that built in a matter of days or maybe a week or 2. But again, basic counters are not always that accurate. They're more statistical recommendations than they are in terms of what's important. The next step that we have is we start taking a look and saying, well, if we want to really get at something that's really important, it's not just a statistical fluke, there has to be some calculation, and that's the entropy calculation, which really gets us at these numbers that we're looking at for something that's an important recommendation or something that's not important at all. Okay, that's what I have. I guess I got maybe a few more minutes for questions. I know I kind of moved through this kind of fast. I'm usually clocking around 1 slide per minute. But again, the whole idea is that you can use this as a reference to go back and take a look at the mathematics, take a look at the code. If you want to see how exactly is this calculation done, that information is there. And that's why I presented this as information, is to try to demystify it for you so you can go back and use it as a reference. Okay, any questions on anything, any of this stuff? Yes?
Given your extended A matrix is really big and complicated, how do your company deal with cold start of new users coming in, has no information at all?
Okay, so those are actually 3 different questions. So let's take a look at them. As a matter of fact, yeah. If you take a look at this matrix, it's growing horizontally. So we know if we multiply this by the transpose, it's going to be gigantic, right? And that's what your first question is, that this gets really, really big, really, really fast. It turns out that you don't have to multiply the whole thing. And the reason is that if I'm doing something like looking at the product views, I still want to recommend go purchase this. If I'm looking at what a person shared, I want to recommend go purchase this. So what we really want to take a look at is trying to get a person to purchase something. So it turns out of that matrix, when you multiply the whole thing out, you're not trying to say, gosh, if I view this product, I want you to go share it. You might want to do that. But again, if we're trying to look at more revenue generating things, we want to say, given these different things, we want to focus on recommending something the person wants to purchase or do. So because of that, most of this matrix gets thrown away. You take this, multiply by the transpose. It turns out only the row itself, which is the same size as the original user height, you might say, is the only thing that you keep. So the rest of it gets thrown away because you're not trying to recommend to share something with somebody. You're trying to recommend and go purchase this. So again, a lot of the stuff that across A transpose A just simply goes away. The second question was on cold start. This is why doing Co Occurrence with an item recommender is very important. If you try to do something with recommending a collaborative filtering where I want to try to find 2 users that are similar, but that means a user has done something that I can compare to somebody else. There's a cold start problem. I have to have some way of saying, well, this guy's just come into the system, they've done absolutely nothing. So how would I compare him to some other user? But instead, with this particular recommender, you take a look at what their behavior is. If that person decided, I'm just going to go view this product, there's a behavior. Other people view that, and bam, right off the bat, you got a recommendation. So there's no cold start problems when you're dealing with this, because you're dealing with behaviors rather than dealing with user characteristics. Anything else? Fascinating thing. And remember that word, entropy. Anything else? Fascinating topic, yes?
Yeah, this is all pretty new to me. I mean, but the math doesn't seem very intimidating. So like, what's the level of effort to kind of get up to speed to do something like this or learn the math fully behind it? Are we talking weeks, months?
Yeah, well, what's interesting is I've been looking at these algorithms actually for years. And the reason is these algorithms apply to many, many different situations. So basically, coming up to speed on the math assumes you have some basic understanding of matrix algebra, which is hopefully everybody remembers that back from high school. When you say, gee, why do we need that junk for? Well, you're going to need that junk to understand bread. So that's what it comes down to. So basically, an understanding of matrix algebra. The actual processing of this stuff into these indicators, the entropy measurements, all you need to understand is what it's trying to do for your data. It's trying to take something that says, we can look at this statistically, how often does this happen? But it's more important to look at this and saying, is this important when it does happen? So if you understand the concept of what that equation is doing, you don't really have to care where it came from. As a matter of fact, that equation itself is fairly simple to implement. As a matter of fact, I think I showed it here. It's just like 6 lines of code. So it's basically, that's all you really need to do. So to understand all this stuff, basically the hard part is you're trying to get all your data in shape. How do you collect all this information so you can start building up all these matrices? Then what it comes down to is, if you're going to implement this on a large scale, then you got to start thinking about, okay, how do you scale this up? But if you just wanted to experiment with it, it's really easy, just run it on your PC. Matter of fact, you probably run a fairly simple recommender on a fairly simple processor, just let it run for a couple of hours. If you want to do millions and millions of products, millions of users, then you have to start thinking about larger scale implementation. So the real problem isn't the mathematics, it's really the implementation in terms of is it going to scale up for what you're trying to do. So all the mathematics, you can see I gave you all the mathematics. As long as you can do matrix multiplication, run it through an equation that is right on Wikipedia, you'll find out immediately if something's important or not. And again, I was using this initially to think about how to analyze data streams. Nothing to do with products, it was relating to SNMP data streams. To say, are we seeing anything important in this? And this was really one of the things I was looking at, is you have all these counters, but they don't really tell you much unless you know if those counters are important. And that's what the purpose of this is to say, hey, there is a way to actually measure something that's important. Yeah. So again, the code is available. I think that was on the slide here. Slides can be available if I can figure out how to distribute them quickly. If anybody else can come up with something besides entropy, I'll give you my USB drive with the code and the slides on it. I was trying to give away that USB drive. Come on. No. Anyways, hey, it's great to have everybody here to see something like this because again, it's not specifically tied to any particular implementation. It's not tied to any particular cloud provider. It's basically a technique which can be used for various types of applications and various types of problems, and that's what's important about this. Again, you have an actor, you have interactions. Those can be anything. For me, it was aircraft and SNMP streams. That's certainly one thing to look at. You can look at this in terms of people buying products, which is what it's typically used for. But you also find some other things too. So people have used this for analyzing fish in the lake. You got different fish and how they interact. So believe me, this can be used for many, many different things. But again, the whole idea is boiling it down to you've got co-occurrences, things happening at the same time. You got all these wonderful matrices that you have to put together, but these matrices tell you something. And then you have a way to say, is this important or isn't it? And getting to that last step is really the leap of faith you have to make in order to really use this technology. Okay, anything else? Cool stuff, yes?
In some of your cases, for example, like the user-based recommendation, actually in data science, in machine learning, it's called unsupervised learning. So there are a lot of libraries in the industry. So in your code, do you use some open source or you just write down all the code from the beginning?
I just wrote all the code. Everything you see here is 10 pages of code. Even the matrix multiplies are that long. It's not that hard to do. The calculations. So you can see this stuff. If you look at the code, these things are all really trivial. Even the g-test score calculation, right here. There it is. There's your g-test score calculation. As you can see, it just simply logarithm multiplies this out, sums it up. Real easy stuff to do. Other things like the cosine normalization, again, fairly simple stuff. So everything you see here is basically in this application that I have on GitHub. So go ahead and download it. You'll see that I don't need anything else to do this. And that's part of the reason why I did it that way, because a lot of times if it's in a library, you may not know exactly what it's doing. This way you can play with it a little bit. This is really the inner loop of the actual matrix multiply, but I modified the inner loop of the matrix multiply to actually find the length of the vectors that it was multiplying so you can divide it and normalize it afterwards. If that's in the library, you probably don't know that that's happening, but you can see it here.
That's awesome.
Okay, cool. Anything else? Okay, that's it. Again, if people are interested in this, actually I think there's some time between this. If you just want to copy the slides and the code from this drive, you can. If anybody's interested.